Okay, so here will be the first part of chapter 5. So here's, in this part we are looking into section 5.1 and 5.2, which are pertinent to, which is related to some basic differentiation operation, including the gradient. Okay, we already introduced special derivative such as curl and divergence in the previous semester, and now we will in section 5.1 we will introduce another special derivative, which is in the form of gradient, and we will introduce the so-called potential. I suppose that you are very familiar with the so-called electrical potential. Electrical voltage, electrical scalar potential. The most famous electrical scalar potential is voltage, 电压, right? In fact, the parameter voltage is a term that we imagine, we formulated to better explain the circuit theory. It's not a voltage is actually not a physical parameter. Okay, that means voltage is not real. Okay, so you probably won't believe it. You probably won't buy it. Okay, I won't buy it the first time I heard of it. But actually, voltage is the product of electrical field intensity and length. Okay, so the actual physical property is the actual physical parameter is electrical field intensity. That's the real one. Okay, but to make our electric circuit theory more easier to explain, easier to understand, we devise the new parameter voltage, so that it's more convenient to develop the electrical circuit theory. Okay, so on top of the electrical scalar potential voltage, we will also introduce another potential, that is the magnetic vector potential. Okay, so you probably do not know that before, but it's actually a very useful tool when we deal with electromagnetic wave problem, the magnetic vector potential. Okay, we will also introduce another few operators, Laplacian. Okay, so that's a combination of special derivative. We made a special derivative twice, and it's referred as the Laplacian. 所以拉普拉斯操作是那个空间向量或存量的微分操作连做2次，称之为 Laplacian. And in section 5.2, we will look into the idea of potential difference and magnetic vector potential officially. So in chapters 2, 3, and 4, we already look into the Maxwell equation in both integral form and differential form. Okay, and in this chapter, we will introduce the idea of electrical scalar potential and magnetic vector potential. And the purpose of this chapter is to lay out foundation for chapter 6 and chapter 7. In fact, the main idea of this semester is the introduction of the transmission line concept, 传输线理论. Okay, the transmission line concept is the foundation for the study of microwave circuit. 微波电路的最基础就是传输线理论，传输线的概念。The transmission line theory is developed based on electric circuit concept. However, as I already said in the previous semester, that electrical circuit is a special case of electromagnetic wave. It's only a special case. What kind of special case? Low frequency approximation. But if you look into the history of the development of electric theory, we have the electric circuit theorem first. Then we found out the existence of electromagnetic wave. Okay, so it seems more easier for you guys to understand the microwave circuits in terms of electrical circuit concept. However, there are some fundamental difference between conventional electrical circuits and transmission line circuits. Because transmission line circuit is often referred as the distributed circuit. So anyway, they are not the same thing. They are not the same thing. Even we use similar terminology to describe the property of microwave circuit, but 他们就不是传统的电路了，所以我当然这是我的责任，要让各位了解到传输线电路跟一般传统电路的那个差别，所以这是本章的一个重点跟准备。Alright, yeah, I already talked about the transmission line theory. So, okay, in the end of this chapter, we will look into the so-called electrical circuit and magnetic circuit. You know, think of magnetic circuit, magnetic field system. The most famous, the most popular example is transformer. OK， 就是变压器嘛，所以你在一个磁耦合线圈的两边放不同的回圈，你可以改变电压。所以 if you look into the configuration of a conventional transformer, you will see that the left and the right are not actually in contact, right? But the energy can go through the ferrite core, the magnetic core of the transformer, to couple into the other side of the circuit. So not only electrical conductor can be used to make circuits, magnetic conductor, such as the ferrite core, can be used to make magnetic circuits. Okay? Alright, so this slide is kind of outlining the topics we will look into in section 5.1. Let me see, okay. We will introduce the idea of potential, and we will then introduce the definition and the operating how it operates for the gradient operator, okay? And then we can express the field, electrical field, magnetic field, in terms of a potential, including electrical scalar potential and magnetic vector potential. Okay, the other mathematic tools we will introduce in this section is the Laplacian. As I already told you, that is you are making the special derivative twice. If you do the special derivative twice, this is referred as the Laplacian operation. And the last thing we will look into in this section is the Helmholtz theorem. Okay, we'll talk about that later. So here's the equation that was shown in example 3.9. That is, this is actually a vector identity. Vector identity, which is valid for any vector. For any vector, if you perform the curl operation first, then the divergence operation on the vector next, you will end up with 0 for all vectors. So that's why it's referred as the vector identity. 对任何的向量，你对它先取旋度，再取散度，它一定等于0。Okay? That is valid for any vector. And So the next thing is the Gauss's law of magnetic field. In the Maxwell equation of differential form, we have found that the fourth equation is divergence of B must equal to 0. Well, for your information, the divergence of D equals to the electrical charge density in the space. Now, this is also referred as the divergence. Okay, whatever. Yeah. Why this is 0 anyway? Because you don't have standalone magnetic charge. We have standalone electrical charge. So as long as you can find a standalone electrical charge, the electrical field built by this electrical charge. If you are looking so this is the electrical field established by an electrical charge, right? So if you see, do we have any difference in the electrical field intensity? Yes. If you look along this way, along the direction that is parallel to the field direction. Question: do you know the difference between the two? 经过一个漫长的暑假之后，你还记得这两个有什么差别吗？一个是 divergence, one is divergence, the other is the curl operator. They are both special derivative. 这个大三角形就是空间的微分嘛，They are both special derivative. However, divergence is performed on the direction along the direction of the vector. And on the other hand, the curl operator is performing the derivative in direction that is perpendicular to the direction of the vector. So it's referred as the lateral derivative. 我有时候习惯把它叫 lateral derivative， 侧边的lateral derivative. Divergence is referred as longitudinal derivative, which is the direction that is in parallel with the vector direction. And, all right. So Gauss's law of magnetic field, we now have the fact that because we don't have any standalone magnetic charge, we have the result that the divergence of magnetic flux density must equal to 0. And if you check up the vector identity on the top, it seems that we can define the divergence of the curve, the vector B is the curve of some vector. We can assume the magnetic flux density B is the vector, is the curve of another vector A, and this vector is referred as the magnetic vector potential. MVP, 什么时候出来这个字？我知道。Okay. All right. And in fact, magnetic vector potential is a very important tool that helps us to solve most of the electromagnetic problems, actual application problems. And for example, for an antenna problem, we assume that you know the current distribution on the antenna structure. You want to know the electrical field distribution in the far field, in the far region. Well, you can derive this directly if you are really good at math. But it's kind of a painstaking approach. Okay, it's not that easy. However, with the introduction of magnetic vector potential, you can calculate magnetic vector potential with integration in the antenna region domain. Now you integrate the current distribution J, you end up with the magnetic vector potential, and the magnetic potential is defined everywhere in theory. It's defined everywhere in theory. So in the far field, you can perform derivative again. Perform the derivative again and end up with magnetic field distribution. So this is not a direct method, but it's even though it involves 2 steps, it's easier to conduct with this method. Okay, so that's the purpose of introducing the so-called magnetic vector potential, which is a very useful tool in handling electromagnetic wave problems. All right, so let's re-examine the Faraday's law. That is, so on the top is the Faraday's law in the form of in differential form. Okay. So we begin with the curl of E equals to the minus of the time derivative of magnetic flux density B. Now we can replace B with what? Curl of A. Okay? So we replace the magnetic flux density B with curl of A and bring that term from the right-hand side of the equal mark to the left-hand side. And because they are, the next thing we do is change the sequence of time derivative and curl operation. Okay, you change the order of spatial derivative and time derivative. Is that okay? Is that okay with you? Okay, good. Thank you for your reply. But why? 为什么我们可以把时间微分跟空间微分反过来倒过来？对，因为在我们所处的时空当中，时间跟空间没有是 decoupled 的，没有交互作用的哈。当然，假如你快要掉到黑洞里头去的时候，这个时候你要去做这个微分的时候，你就不可以交换喽。所以下次要掉到黑洞之前要注意这件事情。OK。或者是宇宙快毁灭之类的时候 ，OK， 不通常应该不会遇到这种事情了 ，OK。好 ，So you can change the order of spatial derivative and time derivative. That's okay. So then you end up with just this 5.2 E plus the time derivative of the magnetic flux and magnetic vector potential A. Equals to 0. And we can identify that, we can, here is another vector identity. It's also valid. And so the first vector identity we have is here, and the other one is this. Okay. So this is the curve of the gradient of a scalar phi. So phi is this mark phi is a scalar. Do you know the difference between scalar and the vector? In the textbook. In the textbook, the vector are shown as boldface letters. 粗体字 okay? Scalars, as shown in the textbooks, as shown in the formulas, they are shown as Italian font. 不是意大利字形啊，是斜体字啊，好不好？斜体字就叫 Italian, okay? They are shown as Italian font. So this means phi is a scalar, 是一个存量。然后这个倒三角是什么？空间的微分嘛。但我们之前讲过，空间的微分有旋度的操作，有梯度的操作嘛，有 curl 有 divergence， 这是对存量的操作。所以存量操作的话，就直接中间没有那个点点或叉叉嘛 Okay. So that's the spatial derivative of a scalar, and it's referred as gradient. Then the gradient of any scalar, the curl of the gradient of any scalar must equal to 0. So that's the second vector identity we bump into in today's lecture. So if you compare the two equations, we can say that the E plus time derivative of A can be represented with as the gradient of a scalar phi. Okay? Is okay to you? Then we can rewrite the equation as 等一下，我们多一个符号，看一下。Yeah, we will introduce the definition of a gradient operator, which will take more than a few slides. So before we doing this, I would like to show this. Okay. Yeah. Here we add a minus sign over here. That doesn't matter. Yeah, because this thing equal to 0, this thing equal to 0 as well. So we add a minus sign. That doesn't hurt. Okay? So if you do this like equation 5.12, you can rewrite the electrical field intensity expression E as the sum of the gradient of a scalar phi and the time derivative of the magnetic vector potential A. So that tells you to produce electrical field. You have two methods to produce electrical field. One is through the spatial derivative of electrical scalar potential phi. Okay, so the official name of phi is electrical scalar potential. 简单讲就是电压了，电压的梯度就是电场，这是你在电路学里头已经学过的东西了，回去想一下。So that's the first way to produce electrical field. Well, to put it simply, it's actually the charge, electrical charge, produce electrical field. It's also produce electrical potential, 电压。That is something that you should be familiar with electrical circuit theory. The second term means not only the electrical charge can be used to produce electrical field, the magnetic vector potential, as long as it has time derivative, as long as the magnetic vector potential, the amount of phase of the magnetic vector potential change with time, then you will produce electrical field intensity as well. 时变磁场产生电场嘛，所以这个时变磁场产生电场的这件事情，我们现在用磁通量密度的不是磁向量位能的时变率来去代表So you write so in this equation you express the production of electrical field intensity in terms of electrical scalar potential and magnetic vector potential, as long as they have a spatial derivative or time derivative. 所以只要它们在空间上，所以电荷在空间中的分布不均匀，会产生电场。有没有听懂这句话的意思？假如说不是说你我要怎么讲？不是说有电荷就一定有电场，是吗？是这样吗？假如你这颗电荷在空间中的分布均不均匀？不均匀嘛，加无加铂嘛，所以它会产生电场。 假如你说每个地方都有一样的均匀的电荷密度的话，有没有电场？有，但是整片都是一样的、啊，好，那个电位是一样的，就没有差别了，好，它那个电位是一样的，没有空间上面的差别，那就等于没有 ，OK， 好，那反过来，你另外一个产生电场的来源是来自于什么？你的那个磁向量位能的时间变化 ，OK， 好，所以那个 phi 称之为电存量位能 ，OK。Alright, so let's go back to the definition of gradient. Okay, so gradient is operator, huh? Gradient is operator that we need to look into for in today's lecture. So, what is the physical meaning of gradient? In Mandarin, gradient is referred as T2. Which means for a scalar, if the distribution of this scalar in the space is not homogeneous, is not even. 假如这个存量在空间中的分布不均匀的话，那么它会有梯度，它的梯度不等于0，它会有梯度啊。For example, if this is the if this is the height, suppose this is a map. If this is the height of a region, then the blue arrow means the change of the height in this region. And by definition, the gradient is pointing to the direction of the scalar is getting bigger and bigger. 你会听懂我这句话的意思？好，梯度的那个定义是那一个存量在空间中的变化是往越变越大的方向。好，从数学的操作上面，梯度的定义是它的那个存量的那个量的变化量是越来越大的方向，是它梯度的方向。所以刚刚我们在前面讲到那个电场的表示式的时候，为什么要多加一个负号？那是历史工业啦，因为我们当初电路学在发展的时候，把电场的方向定义成从高电压的地方指向低电压的地方。那这一个定义刚好跟 gradient 的那个定义是相反的，所以我们只好加一个负号上去。好 ，OK。OK。So phi itself is a scalar. How about the gradient of phi? Is that a scalar or a vector? The result of gradient operation is a vector. Even though it operates on a scalar. Once we perform the spatial derivative of that scalar, we produce a vector. This is the gradient operator. You're taking the spatial derivative of this scalar f in the direction of x direction, in the direction of y direction, and the z direction. The result will be pointing toward the x direction, y direction, and the z direction respectively. So the result, the consequence of gradient operator is a vector. So in this equation, you have gradient of phi, which is the vector, do the dot product of dl. What is dl? Differential length. Okay? There's a vector describing the direction of the path that you are looking into, that we are interested. We are interested in the dot product of the gradient of phi on a specific path dl. 在特定路径 dl 这个方向上面的这个它跟 gradient 的内积。那它内积的结果是什么 ？What is the product of the gradient of this dot product? It's d phi the amount of change in the scalar phi, in the amount of change. So gradient of phi is kind of a rate, a ratio. Okay, so it only ends up with a quantity when it ties with a specific path. Okay, so this is the phi is a scalar or vector. It's a scalar because it's the inner product of two vectors. OK， 所以沿着特定方向乘上它的特定方向、特定路径场乘上它的向量变化率，就会变成是沿着那个方向的变化量，好不好？所以看清楚那些，它们念起来是一样的 ，dphi equals to the del of phi dot dl 啊，但其实它们的意义是不一样的啊，有的是向量，有的是存量啊，请你要小心。OK， the next thing we can do is apply the so-called Stock theorem to the vector of the curl of the gradient of phi, okay? And along a closed path C that encircling a surface region S. Okay, so we do the closed loop integral of the gradient of phi along a specific path C. And once it goes back to the origin, well, actually, the things in the small parentheses is 0 everywhere, right? Because this is the vector identity. The vector identity we introduce in a few stacks. I'm sorry. Okay, so that's kind of the proof, okay, of the vector identity. I'm sorry. Well, okay, because you accumulate the change of phi along a specific path, and this path happens to be a closed path. So you end up with the point or the location that you start. And there is no change in phi, because this scalar phi, as long as this scalar phi is time invariant, 它不会随时间变化的话，你这样绕一圈回来，你还是回到原地嘛。Okay, you return to the original place. So the amount of change equals to 0. So we kind of use this as the proof of this vector identity. And this is, in fact, the Kirchhoff's voltage law that we learned in electrical circuit theory. Okay? So that's the definition of gradient. And here is the definition of gradient in rectangular coordinate system. Okay? The following I already mentioned that gradient is operator, a spatial differentiation operator on a scalar, and divergence and curl are scalar, a spatial derivative operator on vectors along different directions. And here is the definition for gradient in cylindrical coordinate system and spherical coordinate system, so be careful about that. Okay? Yeah, you will find that in your first midterm. Okay? As a credit of me. OK 这是送分题啊，好不好？所以我一定不会考你直角坐标系统嘛，对不对？一定是考柱坐标或球坐标嘛，对不对？所以要小心嘛，要会操作。OK， 好，那我们今天到这边吧，好。